Um, let's wait for the start of the recording. One more second. Okay, so we are online now, and we can start talking about distributed constraint optimization. And there are two reasons for choosing this particular topic among the multiple topics that we could have chosen in multi-agent systems. As I mentioned previously, the field is quite large and developed, and we cannot cover it all. And so we are selecting some specific topics on which we get some general ideas about the field itself. This is again related to task assignment, but it's interesting because it connects with our presentation of constraint satisfaction techniques. Today we will see the version of constraint optimization techniques, and also because there is audio. Why you say no audio? I think everyone else has audio, otherwise just let me know. I do. So, okay, audio is good. Okay, thank you. Thank you, please check. Okay, as I said, this is a good, interesting example of constraint techniques. In this case, it's optimization and not satisfaction. And the other point is that we are also considering a really distributed approach, an approach where the solution is computed by each individual member of the multi-agent system by interacting with the other members only locally. So this is particularly important. For this part, we have material, specific material. It's actually a chapter of a book that you can download from the course website. And we will not cover all the chapter, but we will go to some detail in this algorithm for distributed constraint optimization. Okay. Having said this, let's start looking at the problem. So as I said, this is another instance of achieving cooperation by coordinating the behavior of multiple agents. And in this case, agents are all benevolent. They are aiming at achieving all the same objective. And more specifically, we're talking about the problem which is a task allocation problem. And in this case, we have one example. Here we have several teams for extinguishing a fire, and they need to cooperate in order to optimize the whole process, which is extinguishing all the fires in the shortest minimum time. And the reason for coordination is that they have to distribute over the different parts where the fire is developing, making sure that when there is a big fire, there are multiple units. And when there is small fire, but still need to be extinguished, maybe less units. So overall, the distribution of the task in this particular case is relevant to achieve an optimal solution. Excuse me. The key point, as I mentioned, is that we are going to develop a truly decentralized approach to coordination. Why is this such an important feature of our approach? Well, we are not certainly aiming at a better solution in terms of the quality of the solution. However, with the truly distributed system, we are going to achieve robustness, scalabilities, and to some extent also to some form of problem decomposition, which may eventually simplify the solution in computational terms. So these features are really important when we have a system with multiple agents. In particular, this approach can scale up to large agent systems, and it is robust, because if an agent stops working, the malfunctioning, so to speak, is limited to that particular agent without affecting too much all the rest of the system. While in a centralized system or other structures, a point of failure can have a much larger impact. So here is an example that actually I'm going to show you next week in more detail. So I'm not going to show you the video today. And, this is just to mention that the approach that I'm going to present has also been run on these small doggish robots. So what are the issues in this decentralized coordination? We have that knowledge is distributed, and we want to achieve our goal of coordinating the system without exhausting the resources, namely the communication bandwidth, which is limited, and also the computing power. And overall, it's a complex system, typically, where the assignment is a non-trivial problem. Let's see some examples. But before we do that, let me introduce the terminology. We are talking about DCOP. I mentioned already the meaning of this acronym, which is Distributed Constraint Optimization Problem. And this is the topic of our class today, and it's a well-defined problem, and a problem which is also well-studied. So we are going to see only one of the exact solutions, but in addition to the exact solutions, and there are many such exact solutions, we are going to, we are not going to talk, but you can find in this chapter at least some information about approximate solutions. And so if you want to dig into this topic, this chapter is really a good starting point. And what about real applications? Well, I mentioned already fire extinguishing, which more generally can be seen as incident management. This problem has been studied for tasks of cooperative exploration or for tasks of environment monitoring. As you see, in all of these tasks, the number of agents typically tends to be very high, and therefore approaches like task assignment by contract net are going to be not very effective because of the complexity and because of the number of messages that are exchanged through the network. And the last example is about the grid that are producing electricity, and they need to be, also in that case, they need to be coordinated in order to optimize the energy consumption overall and the energy production overall. Okay, we are going to look at two simpler cases. In particular, here we provide two more concrete examples that we can analyze as a distributed constraint optimization problem. The first one is a problem with surveillance with multiple cameras. We will model such cameras in such a way that they can take only two positions in the environment, left and right. This is, of course, a simplification. It can be much more accurate. By the way, I don't think that the camera here in the classroom is working. Do you see my face, or I don't think so, right? No, that's okay. You can live without my face for today. The face of all the professors are not so important. And here is an example that maybe you're familiar with it, or maybe you are already from a new generation. Here we have Diabolik and Evacant that are in the scope of this surveillance system. And the idea is that the cameras should focus on the areas of the environment where they can gather the most interesting information, where the most interesting information amounts to certainly having a view of all the subjects, but in some cases have multiple views, so to improve the quality of the information for one particular subject. And the other example that we are going to make is an example of a problem that can be formalized as the distributed constraint optimization is meeting scheduling. And also this is an old reference to Charlie Brown comics with Charlie Brown, Lucy, and Schroeder that have to arrange a meeting for playing baseball, the typical activity. And they have other constraints like playing piano, feeding the animal, and the dog, feeding Snoopy, and other things. Okay, again, messages about losing the sound. I hope, again, it's a local thing. Is good, okay, local. So here is the target tracking model as a distributed constraint optimization. We have the two targets of our system, and then we have that the system can have 2 views per camera. And in this case, we have a solution where the one camera on the top left is going to look at Diabolik, and the camera at the bottom is also going to look at Diabolik, while the top right is going to have in its field of view Eva Kant. Now, what is the optimal configuration of these cameras is the problem that we want to solve here. So that's the solution, and here is the formal representation. Typically, we have one variable for each agent, where in this case, the agents are the cameras. So we have 3 variables here, one for each camera, and each variable can take a value which is left or right. So we have only 2 positions for each camera. And the constraints is that we have to have one target. Every target should be under the view of one camera. And then we have what we can see more as a soft constraint, which is a better assessment of some of the targets by using multiple cameras. And the idea is that the overall, the solution to the system should tell each camera in which position to place itself, either left or right, as I mentioned. Let's look at the other example, the meeting scheduling. Here are our characters, and here are the constraints. They want to play basketball, and Charlie Brown needs to feed Snoopy. And at the same time, the Schroeder and Lucy, they have to be together at the piano session. And why this, see on the slide, why decentralized? Why is it so important to have a decentralized approach in this case? Think about a global scheduler. The global scheduler would need to know all the requirements for the meetings of everyone. So a central scheduler needs to know that Lucy and Schroeder wants to be at the piano session, or that Charlie Brown needs to feed the dog, and possibly other constraints. And in fact, what is really nice and important about constraint, using this approach based on distributed constraint optimization, is that each agent will take the decision on what to do simply based on the interaction with the neighboring agents. And this means that there is much more privacy, because each agent will only interact with and communicate about its schedule only with the neighboring agents. So privacy is preserved by this approach. So here the variable can be the starting time of each activity. And see, for example, we have a window from 1 to 8 p.m. in which Lucy wants to play piano with Schroeder, and that the baseball should take place between 3 and 6, and so on and so forth. So determining the activity schedule, the schedule of those activities can be done through distributed constraint optimization. So here you see a different representation of the constraints that are that are considered locally. So for Schroeder, there are only the two constraints, the baseball and the piano. Same for Lucy. And Charlie Brown has a completely different set of constraints. The constraints are expressed as equalities, which are denoted in this drawing by the dashed black lines. And in fact, these are the preferences that are expressed. And so we are moving also in this case with the scheduler towards a distributed constraint optimization. Let me recall what is the difference between constraint satisfaction and constraint optimization. For constraint satisfaction, we are going to typically have hard constraints, namely hard constraints that must be satisfied by the solution. And then we are happy with whatever solution we find that satisfies all the constraints. On the other hand, when we have soft constraints, like in this case, preferences, then we can talk about what is the optimal solution as the solution that better satisfies the constraints. Each constraint is associated with the cost function, and therefore the minimization of the cost of the maximization of the utility, depending on how we want to look at the problem, is the objective of this problem-solving activity. Okay, here we get a possible solution which allows to play baseball at 4 o'clock, and after that Lucy can play piano with Schroeder at 7 o'clock, and Charlie Brown can feed the dog. So after all this introduction, we can, we have more. Okay, these were all information about the sound. Okay. So what is a constraint network? We already know, right? Because we have, it's the same definition that we found for constraint satisfaction problem. So we have a set of variables, we have a set of domains, one for each variable, where a domain specifies which are the values that the variable can take. And then we have a set of constraints that are relations among variables, okay? So as you see, we can have 0, 1 hard constraints that are either satisfied or not satisfied, or we can have soft constraints where a value is associated with every combination of the variables that are participate in the constraint. So for example, in this example with Fi, with two variables xj and xk, the assignment of the value 0 to both xj and xk is the value that maximizes the function in this particular case. Okay, so for the I anticipated, but for the constraint satisfaction problem, the objective is find an assignment that satisfies all the constraints, while for the constraint optimization problem, the assignment, the goal is to find an assignment that satisfies all the constraints and at the same time optimizes a global objective function. And here is how we represent this maximization using this notation with argmax in the sum of the costs, okay? In this case, we can see the cost as utilities, so we maximize the overall utility. So we will focus on graph coloring. There are good reasons for doing so, and first of all, we follow the presentation in this particular chapter, but we are also familiar with the graph coloring problem, and it will be particularly interesting to see a distributed solution for this problem. So here is one example Well, in the formulation that you know, the graph coloring problem is a problem with hard constraints, namely that we want the coloring of the elements in the map such that no neighboring elements are the same color. It is easy to define a version of the problem which is best suited to the optimization problem by associating a -1 cost to each pair of constraints that are not satisfied in the final solution. So here you see one example where you have 0 because all the constraints are satisfied in the leftmost solution. You have -1 since there are 2 yellow neighboring nodes in this graph, and a final case where you have all the nodes are in red, and therefore there are up to 4 constraints that are not satisfied, and therefore a total cost of -4. The constraint, our DCOP solution should get us with 0, the solution with the 0 cost in this particular case. So one addition is that constraints may have a cost. Think about the scheduling problem. You know, the preferences of the dean of the university, of the rector of the university, certainly have a much higher value than my own preferences in scheduling a meeting. And this can be accommodated by simply labeling each constraint with a specific cost value in case the constraint is not satisfied. So you see that in the 2 solutions that are provided on the right, we see that there are 2 there is one constraint that is not satisfied, but this constraint has a cost -2, and therefore that solution is less preferable than the one where the 2 greens conflict, because the conflict between the 2 greens is only -1 instead of -2. So as we said, in making the problem, the constraint optimization problem distributed, we intend to reach a solution by setting the problem so that each agent controls, we say, only a subset of the variables. In all the examples we will make, it's just one variable associated with one agent. This is one of the simplifications that are typically done for making the description of the solution simpler, but in fact it is generalizable. And at the same time, this is the second thing is that we want each agent to be aware only of the constraints with the neighboring nodes. And finally, the communication should not take place broadcast, but should take place only between neighboring agents. Okay? So the one variable per agent is something that can be generalized, but the 2 important elements of this of the solution of the problem is that the constraints are local and the communications are local. There are different ways of measuring the quality of a solution for this problem, and ideally the solution should be optimal, so there is no discussion in that case. But in fact, for approximate techniques, optimality may not be achieved because of computational cost. And in fact, in this case, there are different measures, like guaranteeing that the distance from the optimal cannot be above a certain threshold. Another element for the for measuring the solution is the coordination overhead. Of course, the lower the better, and this cost is the overhead. This overhead is computed in terms both of computation and of communication. So the number and size of messages are the two parameters that we are going to consider also for the algorithm that will be presented shortly. Plus, there are other properties, but we will skip over them. So you already have a general, I showed already a picture with the sort of the general overview of the different approaches. So there can be complete approaches, and we are looking at one of them called DPOP. In fact, in this chapter, you find also the other another approach called ADOPT. This second approach is based on a distributed search, and so on a different principle. While the DPOP that we are going to see, it's going to be based on this idea of dynamic programming, which is being used in many low-cost algorithmic solutions. And then there can be heuristic approaches that employ some heuristics, but they lose the optimality. And there can be approximate approaches that, again, they lose optimality. They may be losing optimality up to a certain point, and they tend to maximize the coordination overhead both in the case of the heuristic and in the case of approximate approaches, namely less computation and less messages over the network. So I already announced that ADOPT is based on a distributed, on a search-based approach, and we're not going to go into the details. And let's see in the overview what is this DPOP, dynamic programming optimization problem. It is based on a technique called the distributed bucket elimination, which is very interesting, and that's one of the reasons, by the way, which bring me to choose, led me to choose this topic in the course. And this is the fact that with this technique, the solution is achieved by doing two passes over the overall node structure. So we will see this in details, but the feature of this algorithm is that the number of steps in order to compute the solution is going to be polynomial. What is going to be exponential can be the size of the messages exchanged. So the exponentiality by this approach is cannot be eliminated because the problem is NP hard, but it can be put in a form that is particularly convenient because it's depending on a parameter which has to do with the shape of the, let's say, of the constraint structure. We'll see a little bit more in details later on. This algorithm is done in 3 steps. In the first step, we need to build a tree. It's called the depth-first search tree. In fact, what is needed is a structure called pseudo-tree, and the depth-first search allows us to build one such tree. There are various ways of doing this. We will see also a distributed way for computing this structure. And then once we have this structure, as I mentioned, there are 2 passes over this, the nodes in the arranged as a DFS tree. The first pass is called utility propagation. And in this pass, the communication goes from the leaves towards the root of this tree. And in this propagation, each subtree propagates the information that in the end will be needed by the root in order to make the decision about its own value. And once the decision, this step of utility propagation has reached the root can make its decision, and the value propagation starts. So the decision taken by the root is propagated down to the children, and the children at that point will be able to make their decision, and so on until eventually the leaves of the tree are reached. Once they are all reached, each variable will have a value that guarantees the optimal solution for the overall problem. So, as you understand, this having reduced the problem to these two phases, utility propagation and value propagation, provides a good framework for achieving a solution. So we are going to discuss the detail of the solution with this problem. In this problem, we have a graph coloring problem, and we want to constrain the problem to use only two colors. You may see this as a little bit artificial, but it's particularly useful in order to show the features of the overall approach. So in the end, we have to decide for x1, x2, x3, and x4, which color should they take in order to optimize the solution, which means that if we have two neighboring nodes with the same color, we have a penalty of -1. And if they are a different color, there is no penalty, so value 0. Okay, so this we want to find how to color the nodes in this with this arrangement using Depop. Okay, this will be our running example. So remember, step number 1, we have to build a pseudo tree. And what is a pseudo tree? Is a tree which has all the nodes that are in the graph, except that these nodes are arranged in a tree structure, starting from one root node, and then being arranged in a structure such that different branches of the tree do not share constraints. Okay, so this is quite important because in this particular example, we see, for example, that x3 and x4 do not share any constraint. And in fact, this in this particular pseudo tree that is being built for this problem, they will be able to handle the messages without referring directly to x1. They will only communicate with x2 once this pseudo tree has been built for this problem. So how is the problem built? It's a procedure for traversing the graph and for arranging the graph so that it will respect the constraint of the pseudo tree, namely that the nodes in different branches, they will not have any constraint in common. And in fact, here we have a description of the procedure. In this visit, we have to, every time we encounter a node, this is marked as visited. And then we keep developing the children of that node. And in particular, when there is a node that has a child who was a parent up higher in the hierarchy, we define a relationship of pseudo parent for that child to the node, to the ancestor. We'll see this through an example, and things will be are more difficult to explain in words than to understand on the structure. So this can be done with a distributed procedure. Okay, let's look at this example. In this example, which is the same as before, I mentioned that this is our running example. We start the visit from x1, and we choose x2 as the next node to be visited. In fact, this is based on a heuristic because x2 has many more constraints than the other nodes. But let's skip for this moment the fact that it's chosen specifically x2. The visit starts from x1, goes to x2, and then from x2 goes to x3, and then x3 does not have any node to go further because x1 has been already visited, being the root, and therefore the visit in x3 stops, and x2 moves the visit towards x4. And at that point, again, x4 realizes that there is no other continuation on an unvisited node because x1 has already been visited. And therefore, at this point, it reports the completion to x2, which again reports the completion of the visit to x1. You see here that the nodes are marked with their starting time and ending time. And you see on the right that the tree has been built with x1 as a root, and the two connections between x1, x and x3, and x4 and x1, they are kept as this relation, which is a pseudo relation in the pseudo tree, which is kept as a relation even though the structure of the tree does not specifically include it. But maintaining this relation is important for achieving the solution of the problem. So here is the first step, and at the end of this step, as I mentioned, we have this tree structure that we can work on in order to do the next two phases. So, as I mentioned earlier, the pseudo tree has the feature that if we take the node x2, this has two children, x3 and x4, but in fact, in order to break the structure in parts that are independent, we need to consider both x1 and x2, which means not only the node, but also the parent, so to speak, but also the pseudo parents of the nodes that are in the two subtrees. So in this case, x1 and x2 will be considered the separator for the nodes x3 and x4, because by removing these two nodes, we have two completely independent structure. Now you see at the bottom, the first one of a series of formal characterization of what a separator is. And let me read this one. We are not going to focus on those writings because the notation maybe is a little bit cumbersome, but we will have to clearly understand what's the concept behind. So the separation is built by taking the separators of all the children, and in this particular case, there are no separators for the children because they are leaves. Then we have to take the parent, which is the letter P, and then we have to take the pseudo parents, and the pseudo parents will be will be x1 in this particular case. Okay. So we have this notion of separation, and then with this notion we can start defining the first phase, which is, or the second phase, which is this utility propagation. As I mentioned earlier, this phase aims at providing for the root with enough information so that the root can make an optimal decision concerning its own value. And the idea is that only the necessary information should be transmitted all the way up to the top. So the utility propagation takes place as follows. Each agent computes messages for the parent based on the messages received from the children and from the relevant constraints, so namely the constraints that are with the neighbor of the node. And the message is going to be a maximization of a specific function which is obtained by aggregating the messages achieved by or obtained by the children and the constraints and all the constraints with the neighboring nodes. Let me move on and show you the formulation for how the messages are computed. Again, we have that the message may be a little bit difficult to read at this stage, so maybe I should first show you the example and then go back to the exact formulation. Here, before I show you the example, you can see the flow of the messages. So we have two messages, one starting from A3 and one starting from A4, that communicate some structure to A2. And when I say structure, it's because what they're communicating is actually a function. And then A2 does some computation, and then it sends another message to A1. And this will be the end of the propagation phase, all the way from the leaves up to the root. Now let's try to understand what are these messages, okay? Let's take one example. This is the example with the message that the node, the agent 3 is sending up to agent 2. We have already seen that the separator in this case is given by the two variables x1 and x2. And therefore, according to the definition, the agent should compute the maximum with respect to x3 for the two functions that determine the cost or the constraint of the constraints between 1 and 3 and between 2 and 3, okay? How to represent this cost? In fact, this is maybe the trickiest part. And in fact, we are going to have functions, and such functions are on integer values. So they are defined only for a finite number of points. Because all of our problem is discrete problem, and we represent therefore functions as tables, and we use the join of this table, the projection of this table, and then the sum of the costs for the entries of the table. And let's see in this example what we are talking about. So remember that we need to talk we need to compute the formula which is at the bottom. And the formula which is at the bottom is going to return us a function of two variables, x1 and x2, right? And this function will be obtained by taking the maximum over x3 of the two constraints f1,3 and f2,3. So let's start by considering what are the constraints f1,3 and f2,3. So look at the two tables that are in the upper right corner. Here we say, well, what happens if I give the color blue to both x1 and x3? Well, since they are neighboring, there is going to be a cost of -1. And similarly for all the other entries of the table. In fact, if we assign blue and red, we're going to have a cost 0. Similarly for red and blue, because they have different colors. And finally, for both red, we again have a -1. And a similar table we have between x2 and x3. So the blue is -1, and so on and so forth. How do we combine these two constraints we have to build a table which contains the value for 3 variables, since 3 variables are involved in x1, x2, and x3, right? So how do we create this table? Well, we replicate the values for in each entry for the 3 values of the variable. So the first line is going to be the pair of values blue and blue for x1 and x2, and the pair of values blue and blue for x2 and x3. And as you see, the table reports the values of these 2 functions and their sum, which in this case is -2 because they're both conflicting. They don't have to be the same color. And this shows a total cost. This particular assignment will show a total cost of -2, okay? So now we have to do the last step, which is maximize this table in terms of x3. So whenever we have the same value for x1 and x2, namely the first 2 rows of the table, what is the best value depending on x3? Well, we see that the best value is going to be 0, and it corresponds to the second line of the large table. And similarly for all the others, we take the combination of, let me see if I can highlight those combinations. Maybe I should be able to annotate. Okay, so here is for the first 2, oops. Too much experimentation here. Here we go. These are the first 2 lines, and the maximum between these 2 lines, according to x3, is given by the value 0. Okay, so we can choose x3 when x3 will be making the choice. If it will choose red, in the case where x1 and x2 are blue, then it can get a total cost of 0. And the same is for the other combinations. So where are you? We have, if we take the table with rows 2 by 2, we can obtain all the values that you see in the table on the bottom right of this slide. Okay, so this table is built by doing a projection operation with respect to R3, X3, and this, getting the maximum values. Okay, so I lost. Okay. I finally got back control over the mouse, so we can move on. And maybe we can go back for a second to this drawing here. And this drawing, you see the flow of the message. We have only computed the message that is going from A3 to A2. And we have to do the computation for all the others. But you see, this process starts from the leaves and goes back all the way to the root. Okay. Now, this is the example with the other message. Once we have a message from, for both messages, u called u from 4 to 2 and u from 3 to 2, then you can compute the value for that goes from 2 to 1 all the way up to the root. And in this case, you have the two messages that are provided by the two children of 2, of the node 2, plus the constraint, which is F12, which is the constraint connecting involving 1 and 2. Okay? So this is for the two values of x1 and x2. The solution, again, we are maximizing by making the best choice according to x2, which corresponds to the first line where we have that if x1 is blue, the cost will be -1, and if x1 is red, the cost will be -1. And at this point, we are at the top of the tree, at the root of the tree, and the tree has this information. What do you think the root can decide at this point? Since the problem is totally symmetrical, it can decide either to choose blue or to choose red. It will be, in this case, exactly the same thing. And we will, we can choose at this point arbitrarily, but we will see in a second through the value propagation that in fact, once this choice has been made, and it's going to be communicated through the value propagation phase to the node x2, then the node x2 will be able to choose its own value in order to obtain a solution which will be an optimal solution, and so on until the leaves are reached. So let's move on to the value propagation phase. We have already mentioned that the root agent computes a value and it sends the message to the children. And this keeps going on, and the children at each step, they have to maximize the information using the information available according to each node according to its own value. And therefore, the message will include the values for all the nodes belonging to the separators that are up in the chain. So here again, we have the characterization of how the value is computed. As you see, this is exactly the same representation that we have seen earlier. Namely, we have the constraints with the children and the pseudo-children, and we have the messages that are received by the nodes that are children. So messages plus constraint. And in this particular case, this is, not in this particular case, it turns out that these structures that we are computing are exactly the same structure that were computed in order to bring up the message towards the root. And therefore, they can be reused. Let me show you how. Here is the flow when they go from the root to the leaves. So we have a message from 1 to 2, and then messages from 2 to 3, and from 2 to 4. So here is the starting of the value propagation. Here we have a root again. The root needs to choose its own value. As we said, in this particular problem, it will be the same, choosing blue or choosing red. Let's assume that the root chooses blue, and then at this point transmits the value blue to the node x2. And x2, knowing that x1 is blue, can in turn choose what value to take. So if x2 will choose B, then the value will be -1. And if the x2 will choose red, then the value will be -2. And in fact, it turns out that this is exactly the same table that was used in order to compute the message to be transmitted to X1 in the utility propagation phase. So we have two choices already. We have X1 and X2. They are both blue, and this will provide a total cost of -1. Well, this is according to our intuition of the problem, right? With two colors and with the constraints that we had in our problem, we could not find a solution where all the neighboring nodes had different colors. So let's see how the process ends. We have one more step. After having chosen blue for X1 and X2, then this information is propagated down. And at this point, for the node X3, for example, there are two lines where there are both blue for X1 and X2. And in these two lines, we have a -2 cost, and we have a 0 cost here. So eventually, X3 will choose the color red, so to obtain the maximum value, which in this case is 0. And in fact, the constraints between X3 and X1 and X3 and X2 will be both satisfied if we do this assignment. And the same type of table, the same type of message will take place for X4. And here we go with the final solution that we have obtained. We have X1, which is blue, X2 is also blue, and X3 and X4 are both red. And we obtained the optimal solution with only one constraint violated. Okay, I hope that this presentation gave you an intuition of this algorithm. And I think we are about close towards the end of this part of the class. We have only some recap. First, we want to say that the computational analysis of DPOP shows that the exponential has been pushed into the size of certain messages, namely these tables that we have that are transmitted can be exponentially large, where the exponent is the number of variables that are in the separator, essentially. And the maximum will determine the complexity of the, and in fact, this corresponds to it's determined by computing the induced width of the DFS3. Let's forget about these details and let's remember that the problem, computational problem in DPOP is the exponential size of the messages. So different DFS3s can therefore provide different solutions in terms of efficiency, but finding the optimal DFS3, or better, finding the optimal pseudo-3can be NP hard, therefore an approximate solution is in order. And finally, okay, yes, here we are. And finally, recap, very quick. Distributed constraint optimization is another approach to task assignment. And it's particularly interesting because the solutions are truly distributed, namely scalable, robust, and in particular, the distribution also is privacy preserving, which is also particularly important for this type of for many type of problems. And we have been gone in depth on the DPOP algorithm, which is one of the most efficient solutions for this problem, where the exponential nature of the problem is reflected in the exponential size of the messages, while the number of messages is linear, and the problem is arranged in such a way that the nodes are considered only twice in the overall computation of the solution. Okay, I think I will stop here and check whether maybe we want to stop the streaming. at this point. Maybe we will start for the next section. Before I do the stop of the streaming, is there any question about this?